Hello again, and if you don't know already, I'm Florence, and just now I'm going to be explaining what Feynman diagrams are. But before we get started with that, we really ought to know who Richard Feynman was. And Richard Feynman was a brilliant man. He was the person that invented Feynman diagrams, and he also received the Nobel Prize in Physics. As well as that, he participated in developing the atomic bomb, and also, at least I think, he's really good at giving lectures, because there's plenty of them accessible online if you're interested in having a look. Now before we get started, you really ought to know what antimatter is, which I explain here, and what quarks and leptons are, which I explain here. If you're unsure about any of the language that I use in this video, do check out these videos because it's really much simpler than you think. And this is going to be another video where we go up to the whiteboard, so here we go. Right, before we get into this, I need to explain to you what a Feynman diagram is. And essentially what it is something that shows the interactions between particles. Now I could try and explain it, but really the easiest way to do it is to show you, and that's why I'm up at the board right now. So if you've made it this far into the video, really you ought to know what electrons and positrons are. So I'm going to do an example of a collision between an electron and a positron, and I'm going to demonstrate this using a Feynman diagram. What we have is an electron and a positron down here at the bottom, and they both go up towards a point where they collide. And across here is space, so if you just look at it in the horizontal direction or the x direction, all they are doing is travelling straight towards each other. But they aren't going towards each other and colliding instantaneously, they travel towards each other, and that's why the y direction is time. And when this electron and positron collides, they form a photon for a short period of time, which I've emphasised here. And in the most simple circumstance, the electrons go in and then they come out again as another electron and positron. And that's a very simple example of an electron-positron collision being demonstrated on a Feynman diagram. What it's showing is, if you look in the x direction, the electron and positron collide, form a photon, and then they travel apart from each other. If you look in the time direction as well, you'll see that they come closer and closer together until they eventually collide, form a photon for a short period of time, and then they travel away from each other. Because if it was just in the x direction, it would just all be overlaid and anything could be happening at any period of time. The y direction allows us to see what order things are happening in, because these can get awfully complicated. But to steadily get more complicated than this, the electron and positron, when they collide, don't always form an electron and positron when they come out. For example, they could form a muon and anti-muon, which again, if you don't know, check out the videos that I suggested that you watched at the start. Anyway, as you should know, muons have more mass than electrons. So how can two electrons collide and then form two things with greater combined mass? And that's where E equals mc squared comes in. And if you want proof for that, click somewhere around here and you'll be taken to that video. But anyway, because energy is equivalent of mass, these electrons could come in with a higher kinetic energy, basically meaning that they're travelling at a very fast speed, so that when they collide, not only is the photon produced the energy equivalent of their masses combined, but it's the energy equivalent of their masses and their kinetic energy, meaning that this photon can form particles with a higher energy than the mass of the electron and positron combined. To make it more clear what I'm saying, I'm going to redraw this so it's more appropriate. So you have an electron and a positron which quickly come together and collide over a relatively short period of time. They then form the photon, which, as you've noticed, is shown as a squiggly line to show that it's just electromagnetic radiation. And then this photon forms different particles, and in this case it is a anti-muon and a muon. As you've noticed, I've done these lines at a very shallow gradient to show that they are coming together over a very short period of time, so they're moving at a very fast speed. And up here, the gradient is steeper, showing that they are travelling at the same distance over a greater period of time. Because these particles afterwards don't have as much kinetic energy as the initial electron and positron, because some of that kinetic energy has been converted into mass. But I should also add that this electron and positron don't have to form more leptons. They could go off and form a quark and antiquark, for an anti-up quark and an up quark. But we're going to stick to a anti-muon and a muon for now, because they are of most similar mass to the electrons. Here it starts to very slowly get a little bit more difficult, because this electron and positron, when they form the muon and anti-muon, it's not necessarily the end of the story, because up here, what can happen is something else is produced as well, branching off from one of these. And that can be something such as another photon. There's a chance that something such as a photon will be produced, and the chance of that happening is called the fine structure constant. And that's just the numerical value of the probability that this will occur. And the way that we write that is alpha with subscript em. And for example, for a photon to be produced when an electron and positron collide and form a muon and anti-muon, the chance of the photon being produced is about a fine structure constant of 0.01, meaning that for about 1 in every 100 collisions of this sort, one photon will be produced there. Just imagine it's the probability of a sub-branch growing out of one of these branches. I should probably have added this earlier on, but when an electron and positron collides, there's really three main possibilities of what will happen. Either a lepton and its antipart will be produced like you see there, or a quark and its antipart will be produced, such as an up quark and its antipart, the anti-up quark, or quite simply a jet of hadrons will be produced. But just as a photon is the quanta of electromagnetic radiation, something else can be produced in these circumstances, and that something else is called a gluon, which you draw as a sort of spring coming out. And as I said, just like the photon is a quanta of electromagnetic radiation, meaning that it's essentially a piece of electromagnetic radiation, a gluon is a quanta of the strong interaction, because what a gluon does is it sticks the particles inside the nucleus together. The gluon sticks particles together very strongly, but it only really applies over very short distances. And I should add that the strong force is so strong that 100 giga electron volts of energy, which on these scales is a heck of a lot, will only separate a quark and its antipart by about 100 times the size of a proton. Now perhaps you've noticed that when one of these particles emits a gluon or a photon, its flavour doesn't change, and that's because the only thing that does change is the strength of the strong interaction in that case. Everything else just stays completely the same. Now this sort of thing can lead on to some rather interesting stuff in string theory, which is basically dependent on the number of times that, for example, an electron and a positron come together and form a photon, but they could also then go out and form an electron and a positron again before going back in to form another photon, and so on and so forth, before they eventually form some other particles. And the number of times that happens in string theory is called the string coupling constant, which actually leads to some rather interesting stuff when it comes to extra dimensions, or more specifically M theory. But that's something for another day, and I think I've been talking for quite a while now. So I will leave it there, and perhaps I'll start making a different video, something that I can upload some other time. So if you have any questions, suggestions or corrections, please leave them down in the comments down below. As many of you will have noticed, I do aim to respond to every comment that people post down below, so that you don't feel ignored. And All of your suggestions really do help. For example, my video on superpositioning was done entirely because of a suggestion down in the comments. But otherwise, thanks for watching, and I will see you next time. Hello once again, I'm Scott Florence, and if you don't know already, I'm Scott Florence. Nope, that's wrong. How can I get the starting thing wrong? Oh well, here we go again. Just now I'm going to be explaining what Feynman diagrams. Hello once again. I can't remember if it's Feynman or Feynman. I think it's Feynman. Hello again, and if you don't know already, I'm Scott Florence, and just now what I'm going to be explaining is what Feynman diagrams are. Okay, I just can't talk right now. If you want proof for that, click here. Interrupted by a phone call, but anyway, let's keep going. Where was I? And I'm going to demonstrate this using a Feynman diagram. I'm going to speak properly. She sells seashells on the seashore. It sticks the quarks inside. No, yes.